Alright, let's do the next problem. It is still in section 5.5. It is a non-inverting configuration again, because if you look at it, is terminal or the non-inverting terminal. Okay, then of course there is this negative feedback configuration. The output is tied back into the negative input of the operational amplifier. Okay, so let's begin by working on this. So what are we supposed to find? Okay, we are supposed to find the value of VO, output voltage. So plus minus VO. What is the value of the output voltage here? That's what we are supposed to calculate. Okay, that's the first part of the problem. VG is given to be 3 volts and all the resistance values are given. And let me make sure that the terminal, the power supply voltages are plus 10 and minus 10. And this is problem 4.20 from the textbook. Okay, now let's see how can we solve this problem. Of course, the second part of the problem is to find the range for linear operation. Let's start with problem part A of this problem. Okay, part A of this problem, solution. We are familiar with this. It's a little different. The reason I picked this problem is this is slightly different. Okay, we are typically used to writing KCL at this node Vn, right? However, in this problem, we don't know Vn, okay? But how do we know Vn in other problems when it is not given? We use Vp value, okay? So the first step in here is to calculate the value of Vp. In the earlier problems, Vp was either tied to ground or a direct voltage was applied to it. We never had to maybe once or twice, but not often did we have to calculate the value for Vp and then plug it in to the value for Vn. But here we need to do that. Okay, let's see. In this scenario, notice that the current going into this branch is 0. IP is 0. That's the current constraint, right? So because of the current constraint, the current going in there is 0. So what we have is the current coming out of this voltage source passes through the 30 kilo ohm and 45 kilo ohm resistances, and Vp happens to be the voltage divider. Okay, think about this. What Vp is a 3 volts. That's Vg. Let's write it as Vg. Let's keep it as Vg. Okay, Vg, and then 30 kilo ohms, and then 45 kilo ohms. Okay, kilo ohms. That's Vp. So Vp should really be the voltage division 45 kilo ohms divided by 45 plus 30 kilo ohms. Okay, so that comes out to be 0.6. I think it's 0.6. I could be wrong, but 45 kilo ohms by 75 kilo ohms. Okay, now let's see. What else we got? We have Vp known. So now we can apply step number 1. Okay, we can apply step number 1, which is to apply KCL at node Vn. Okay, we can apply KCL at node Vn because we know Vn. Okay, from step number 2, we know Vn equals to Vp, which is found out to be 0.6. Okay, times Vg. Actually, there is a factor of Vg over here, 0.6 times Vg. Okay, so that's the let me show this multiplication multiplied by Vg term there. Okay, 45 kilo ohms by 45 plus 30 kilo ohm is the factor that multiplies Vg. Now let's see. So Vp is Vn is 0.6 Vg. Now we can apply KCL at node Vn. Okay, at node Vn, applying KCL here, this is Vn minus 0 by 15k, and then there is this current which is Vn minus V output, because the other terminal is connected to V output, okay, over 48k. Okay, let's see, let's plug that in, and there is no current flowing here. The current flowing here is 0. So let's write them out here. Vn minus 0 over 15k plus, do you remember the other expression, Vn minus Vo over 8k, all of that turns out to be 0. So that is the application of KCL at node Vn. Right? So now what happens is, we can simplify this. Vn over 15k plus Vn over 48k equals to Vo over 48k. Okay. Now we know Vn, we have seen Vn, value of Vn is what? Is the same as Vp, which is 0.6 Vg. Okay, so this is the expression for Vp, this is the value for Vp, which is the same as Vn. Okay, so plug that in there, 0.6 Vg over 15k plus 0.6 Vg over 48k equals to Vo over 48k. Okay, so simplify this, we'll get something like 2.52 Vg equals to Vo. Okay, that is the mathematical manipulation. Do the mathematical manipulation, that is what you would get for V output value. Now in the first part of the problem, Vg is given to be 3 volts. That makes Vo equals to 7.56. Okay, 7.56 volts. Now the next part of the problem is find the range of Vg such that it is in a linear region. This is something straightforward. We have done this multiple times. What did we do? Vg or V output really should be between plus VCC and minus VCC. Okay, this is negative VCC and plus VCC. Okay, plus VCC. Of course, the negative VCC is negative 10 volts, negative VCC, and the positive VCC is plus 10 volts. Okay, pretty straightforward. So VO, I know I can write it in terms of VG, right? 2.52 VG should be less than or equals to negative VCC, which is really negative 10 volts, should be less than or equals to, you see where I'm going with this, right? Plus 10 volts. Negative 10 should be less than or equals to 2.52 VG, which is in turn less than or equals to 10. Okay, now I got this V output equals to 2.52 VG earlier. Okay, that is how I plugged in a value of 2.52 VG. Okay, matter of fact, I'm lazy bit. I'm just going to simplify my equations by dropping that 0.02 term. Okay, the division becomes straightforward. Okay, so negative 10 volts over 2.5 less than or equals to VG, in turn less than or equals to 10.5. All I've done is to divide both sides of the equation or all the terms by 2.5. So it turns out that VG should be greater than or equals to negative 4 volts, which should be VG should be less than or equals to positive 4 volts. As long as this condition is satisfied, okay, the op-amp is going to be in saturation region. Okay, so this condition ensures, linear region of operation. Okay, as long as once your VG value crosses these limits, that is when the op-amp is going to saturate at the positive VCC or at the negative VCC. Pretty straightforward problem. All right. So that completes our discussion on non-inverting amplifier. Okay. Think about this. It is called a non-inverting amplifier because, pay very careful attention, what's the value of VG? Positive 3 volts. What's the value of the output voltage? Positive 7.56. Okay, the output has the same polarity as the input, hence the name non-inverting amplifier. Okay, this completes our discussion on non-inverting amplifier. We are ready to move on to section 5.6, which is difference amplifier. See you there.